Hey guys! Today I will explain what hash pointers are and how they are used in blockchain projects. So a hash pointer is actually a data structure that points to a place where the information is stored. So I can ask to get this information back and verify that it hasn't been tampered with. For blockchains, this is very important to feature because they need integrity and validity to actually be secure and be trustworthy. In short, a hash pointer tells us where something is and what its value was. And we can build a type of data structure around these hash pointers. So now I'm going to actually talk about an example, which I'll show you here in a bit. And in this example, we have a data structure called a blockchain. On this top, we have the H, which refers to the previous block data. And on the side, we have a linked list. So you have all these blocks stacked to each other, and they have all these links recording to the previous hash pointer. So the data links to the hash pointer. So if we want to store this list, we can store the head of the list. So that's all the tops, which are the hash pointers. And we can log all these transactions in a fast and easy manner. So you can just build a sort of Merkle tree, what I will show you guys in a later. And we can also detect if someone altered the data in the block. So because of the data is listed to a hash pointer, you can see if someone altered the data, so then the hash pointer will be different. Someone can actually change all these hash pointers and data structures, and then the whole data block is actually tampered. The one thing that stays the same is the top H here shown here, and that can't be tampered with. That's set in stone. So you automatically know that someone has tried to tamper actually with this. And that is a very important thing about this data structure, because you can really see and fast that someone has been tampered with the data. A good overview actually to see this is a Merkle tree. And you see very easy how they are linked together. So in the picture here, you can see the hash pointer pointing to the data, and this happens multiple times. So you arrive at H and you have all these steps. So you have two blocks, and then they point to these, and then the data goes back. So that is really important. So what if someone actually tampers with this hash pointer, which is linked to this data? It will go up the chain, and you will see that this data has been tampered with, and he will hit a roadblock once he actually comes to the head of the list, which is called the root. Just by remembering this hash pointer, we've essentially remembered a kind of tamper-evident hash of the entire list, and all the way back to the beginning, which is very important because then in the Merkle root, you see all the way to the top. If you follow back the transaction, you see that what is here doesn't match what tells the data what is there. So you can see it in an easy way. So in this example, I'm going to be talking about a binary tree with hash pointers. And this is also called the Merkle tree, which I just talked about. Advantage of using a Merkle tree is that we remember just the root, and if someone wants to convince us that this block is in the Merkle tree, they need to show us the block. And if someone tampers with that block on the bottom, the hash pointer on the top level won't match. So we have to tamper with all the hash pointers of the upper levels until he arrives at the root of this picture, and he won't be able to tamper with the root of the Merkle tree. So any attempt of tampering with it, with the data or in the hash pointers, is nullified because he can't change the top. And in Bitcoin, this is the Genesis block, and you cannot change the Genesis block. It's in the software, and that's why if a transaction can be faulty, if you look all the way back, he cannot change the Genesis block, so we automatically know that the block the person added is not a valid block. And then you can scrap the transaction and go to the longest chain, and all is good again. So in short, a Merkle tree has several advantages. The tree holds many items, but we just remember the one root hash, and which is only 265 bits. We can verify membership in a Merkle tree in a logarithmic and time and space, which means if we want to prove that a block is a member of a Merkle tree, we just have to show the amount of data, and then it takes about log n times for us to verify. And so at a very large scale, it still goes relatively fast because it works in log, and that means the time will decrease very fast when you want to verify a lot of transactions. So it will not take an eternity, even though the chain can be 300,000 blocks long or even longer. So using a Merkle tree with hash pointers, you get a visual idea of how the data has been tampered and how resistant the data structure is. So I hope you guys have learned something from this video, and thank you guys for watching.